Let's.
Yeah, that's like a meme, like the UCs, because they already canceled classes, so they're all online, and they said, they have like a comment section.
Yeah.
Because they don't on Zoom. Can you go to the restroom?
Yeah.
They say, yeah, sure.
Well, you can spread viruses through the internet too, I've heard. So there might be like a COVID, whatever.
New coronavirus?
I virus. All right, so Stork amine reaction. So this is the nucleophile. Sorry, I forgot to start recording this, guys. Test is on Wednesday in case you picked it up just now. This is your nucleophile now. And so then you can have your electrophile as is, and then the mechanism for the Stork reaction is just like that. So that's how it acts nucleophilically. And it only happens the one time, and you can control which one's the nucleophile. It's not under conditions that will promote the aldol reaction of this, although it could still happen. You can still get some of it. So then what happens is when it's all said and done, you're going to end up with this guy as your product.
Oh, then you're throwing it off, right?
And yeah, and then you use like H plus and water.
Oh, you would have to take it out of the solution.
Yeah, so you end up with this after this process, right? And then you're going to do H plus and heat and water and heat it. And the only drawback to this is if you want to have the alcohol, you're not going to end up with the alcohol. I think you're going to end up with this.
Oh, this is the way.
Because you're heating it with acid, and
Well,
it'll cause the condensation reaction to take place, I think.
can you just add H2O? I mean, just H2O? With a double bond?
Yeah, but it won't end up where it is.
Yeah,
I mean,
it won't end up where
it'll end up over here.
Yeah.
You could do something with the
peroxide.
bromine. Maybe peroxide HBr might work with that. I'm not sure actually with the alpha beta unsaturated. But anyways, yeah. But that's what you'll end up with most likely. I don't know for sure, but that's what my gut feeling is for that. All right. So then the last thing that you can do, right? You can use LDA. So so did I write down what we were actually doing here? Make the nucleophile an enamine. Yeah, so I did that. That's we use the Stork reaction. And the third thing that you can do is use LDA to convert the convert one of the aldehydes to the enolate. And that one will be the nucleophile. And then, so what they usually do is they take LDA and they'll add it to the, or take the LDA in solution, add the aldehyde to it and form the enolate from it. So there's always, like, as you're adding it, there's an excess of LDA and a limiting, then basically no aldehyde in solution as you're adding it. Right? Does that make sense? Have the strong base in solution, and then you add the aldehyde that you want to make into the nucleophile into that. As it goes in, it converts over to the enolate, and there's no aldehyde in solution for it to react with. If you do the other way around, you put the aldehyde in solution and you put the LDA in, you're going to be converting it over, and then little by little, it'll be reacting in the solution. So it'll be reacting with itself. Right? That makes sense?
Yeah, because you did one way, it'll react.
Yeah. So
the other way is already there, so everything comes in.
Yeah, you have an excess of the LDA, so it completely removes the aldehyde from the solution as the aldehyde goes in, and then you just keep adding it until you have about equal molar amounts of the two. And then what you do is you add in what you want to be the electrophile. So this is the first step. So you use LDA, and the second step is you add the electrophile. Okay. And that should help control like the reaction in terms of which one's nucleophile, which one's electrophile. So these are pretty common things, and I'm going to talk about these also in the context of other reactions. But basically, it's the same steps. Okay, so next kind of reaction, a lot of different kinds of reactions. This is known as a Claisen reaction. Yeah, and a Claisen reaction is, how do I want to do this? Yeah, I'll just write out in words. 2 esters, and then you get a beta keto ester. Okay, and then I'll give you an example.
Wait, what? You get 2 beta?
So you get 2 ester molecules, and then what your product is a beta keto ester. So, and then I'll write out an example. I'll do a simple one. What's a simple one? I'll do like, I'll do this one. So I'll do that. So I'll have 2 of these. All right, and then the base that you use is specific to whatever the ester is. Okay. So the base for this one would be this, like NaOCH3. So methoxide, sodium methoxide would be the base. And the reason you do that is because when you put a base in solution with an ester, you can get like cross esterification reactions where you form a different ester. Not cross, what do we call that? Transesterification, when you form one ester from another. And so if you use a base where the OCH3 is exactly the same, that reaction might take place, but it doesn't matter because it's the same group. Okay. And then what you'll end up with is this, actually, let's see. Oh, let me write it out again like this. And this is alpha and beta. So this is a beta keto ester. Like that. All right, this is a ketone. This would be the keto group. So that's where that terminology comes from.
What happens? There's 2 esters on each side of the ketone, and you just say, let's just say one was like a apple next to it, but the other one had like a purple or something in that, and you only want the purple to react. So your base has to be the purple.
Oh, yeah, you'd probably make the base propyl, but you'd have to do some other things to it to make it work. So let me get to that when I get to that part in the lecture. Let's see. So mechanism, let's do the mechanism. So what's the first step? Formation of a enolate ion, right? Yeah, so that'll be your first step. And often this is called base promoted reaction because it's not really catalytic. So you'll end up with, I'm going to draw this molecule itself real quick with the hydrogen present, and then C double bond to O, and then OCH3. And then I have OCH3 minus in solution. This is the base that we use to promote the reaction, and that it'll form the enolate, which will look like this. And so then that's causing this series of arrows to form. Again, I'm saving laziness, cold. I could have put the pair of electrons there and drawn the resonance structure.
But that happens first, right?
No, it's good to know that though.
The base happens first.
Yeah, first step is the attack of the base, and that creates our nucleophile. And then, starting with the nucleophile on the right, unfortunately, because of the way I've drawn this one, it'll look like this. I'll draw the other molecule in. So I'm going to go so this is my enolate ion, and then I'm going to draw the other one over here. It'll be CH2 or CH3, sorry, C double bond O and O CH3. Yeah, this is my alpha. That's the nucleophile, right? And it goes there, right? So what I'll end up with is I'll end up with something that looks like this. Sorry, that'll go up. Computer is like burning up. You hear the fan just like, I'm on fire. Like that. Then what happens? Like looking at the product that's like 2 lines above, what must be happening?
Oh, and then the acid, I think it's taken away.
There you go.
Because the base that's the acid formed from the HOCH3.
Now looking at this, right?
Oh, but it kicks it out of the leaving group, yeah.
Yeah, this is a leaving group now, and this is why it's a special reaction, because you do have a leaving group as a. Unlike when we did the aldehydes and ketones, we have this leaving group that can leave, right? And so this happens. And that, although it doesn't quite look like it, gives us that. That's what I was talking about. Well, a couple of notes that are important. Actually, there's a workup step in between here and here, because what happens in the solution before you can finish this part is that this hydrogen is actually acidic, and so what ends up really becoming the product, the intermediate product before you get to the product, before you work it up, is actually this guy. Let me draw it like this. So actually in solution, what you end up with is something like that. And it turns out having this be pulled off helps to pull this reaction in the forward direction. It essentially removes this from the products and then causes this to form, right, in the process. And just like we learned from like Chem 1B, the Chatelier principle, anytime you can pull the product out of solution, right, even if it's to form its enolate ion, you force the equilibrium to the right. So this is fairly acidic. This is under fairly basic conditions. And so this guy gets pulled off here and forms this. And that helps to form the product. In fact, from everything I've read, if you don't have these alpha hydrogens present when the reaction takes place, it's not stable enough, and it does what's called a Retroclaisen reaction. It just falls apart. It dissociates again. So you have to be able to lock the product in by having an alpha hydrogen in the position here between the 2 carbonyl groups, okay? So this is necessary. Alpha hydrogen in the product is necessary for good product yield. And there's something called a Retroclaisen reaction. And the Retroclaisen reaction is actually just the opposite of this reaction, where you form this product here that we said, oh, sorry. You form this product here, and then the nucleophile comes in, which would be the OCH3, and decouples it to these molecules again. Right. So it undoes this bond formation by attacking at that point here. So that's generally not what you're trying to do. You're trying to get a product out of it. So we generally try to have that alpha hydrogen present. Some notes. Yeah, so we call this I'll just write these out. I don't have them exactly in this order either. It's a promoted reaction, not catalyzed. You'll see this a lot, this term a lot. And it's promoted because the hydroxide makes the base makes the reaction faster, but it's used up in the reaction. When we use hydroxide, it's hydroxide catalyzed because the hydroxide is always regenerated in the reaction. So this base is used up during the reaction. Not a super important point, but I don't want you to be confused by terminology when I say it later. Alpha hydrogen has to be present in product. For good product yield. Let's see. Oh yeah, the third thing, and that's actually the first thing that I talked about, is the base used matches the OR group in the product. So you have different ones, right? But you want a specific one in the product, you just use that one.
For the product? For the reactant?
No, you want it in the reactant because or in the product, because that you might substitute that one out. Does that make sense?
Yeah, but don't you have to use the one that practices the reactant so you can get the product?
Yeah. So here, let's see where we right. This is just acting as a base.
Yeah.
Right. And it could substitute this, right?
Yeah.
It does, but it doesn't matter because that one gets ejected.
Yeah.
Right. But it could it could also substitute this one, and whatever this one is really the one you want to keep. So that's the one you should have in the solution. That's the one you should be putting in. So you should be starting with that, right? That, and then if it gets substituted and you're using the same base, it'll come out of the product too.
Oh, never mind. That's what it is.
Okay, good. I don't know what I'm not sure exactly what you were going to say, but
Can you scroll down a bit so I can get number 2 done? It's a bit too much.
Too much? Back a little bit? Is that more helpful?
Yeah.
Because that wasn't my goal there. Do you want me to shrink it a little bit so I can get it all on the screen at one time?
You get it on the test?
Okay. So, product control, right? Because you can do mixed Claisen. I'm not going to do an example of a mixed Claisen, but you can do mixed Claisen reactions. One ester should have no alpha hydrogens. This is the same thing we did for aldol. If you have an aldehyde with no alpha hydrogen, or a carbonyl group with no alpha hydrogen, it has to be the electrophile, right? must act as the electrophile. And then, ooh, sorry. We're okay. Kind of it's freaking out on me because it's getting so hot, I think. Nope. So then the second thing is the base. Must act as, and then I have base should mask ester without alpha hydrogens. That one you can't read, I'll actually. I'm going to check that one. I think I have that backwards. And then the base. With alpha hydrogens should be added slowly. Yeah, actually, I'll show you something here in a second. Let's see. I did that one. There's some example problems in here, but I don't know if I have time for them. If I do, I'll come back to it. Gosh, I thought I had some other sort of important examples in here, but I don't see them. Maybe they're later. Oh yeah, they're later. Okay. Ester, Retroclaisen. Okay, so that'll be, well, if you die, we'll make it in your honor. But it would be awesome. Not that you died, that you had a poster, like the Immortal Carol.
Oh, no, I was down to die, but
No, you still have to take physics. I'm sorry. You have to finish physics and math before you can die. Sorry, you're gonna have to. Okay, intramolecular Claisen reaction. So these usually happen between 1,6 and 1,7 diesters. So I'll do an example of a 1,6 just for fun. It's this reaction. So 1, 2, 3, 4, 5, 6 like this. And then RO minus is the base. And then the product will actually be, and then we'll run the mechanism for it. The product will actually be this. It doesn't really matter which one you pick. It's symmetric in a sense, not truly symmetric because one's going up, one's going down. It's symmetric in the sense that I have I have esters at both ends, right? And I could have substituents on here. So let's just for fun, we'll add that in. We'll add a substituent in later. But what I normally do when I do these is, again, I count, right? and I count from the nucleophile to the electrophile. But I often, on these ones, only count from the nucleophile, nucleophilic carbon to the electrophilic carbon, and then I add substituents to it. So if I pick this one as my electrophilic carbon, I go 1, 2, 3, 4, 5, like that. Then what happens is 1 attacks 5, and that gives me my 5-membered ring. Okay. So the first step is going to be, we need to form that enolate ion by adding a base. So I'm just going to start with that. Okay. And then it attacks, and what you end up with is you end up with something that looks like this. And it's going to be a 5-membered ring. So the reason I draw or I count the numbers between the nucleophile and the electrophile, that tells me the ring size. Yeah, so it'll be like 1, 2, 3, 4, 5, and then I number it, right? So this is going to be 1, 2, 3, 4, 5. So in the mechanism, then I end up with O minus here, and then an OR leaving group like that. And then that collapses, and the OR group is ejected like that. And takes me straight to my product, which I've got turned. So I'm going to add a substituent in a different color, isopropyl. Why not? I'll add it. Which carbon should I add it to? Not 1. 3? All right. Right, so in your product, it would be here. And that's the purpose of numbering, because you just need to know where the substituents are on the ring for these. And so I just numbered. In my notes, I numbered more carbons, but that's fine.
So this happened like without anything else?
Yeah, because it's its own, it's like its own nucleophile and electrophile. It's kind of like a worm, right? They're like, make babies by themselves. I don't know. Is that weird? What? You don't know this about worms?
Yeah, yeah.
And
don't you like cut them in half or something? There are, what do you call it? It starts with H.
Hermaphroditic.
You have the girls and then, they're girls and then guy organs, but when the worm comes together, they enter.
Oh, so the two, they still need a mate.
Yeah, they still need a mate, but it's but
I didn't know that about worms.
Yeah, it doesn't matter what kind of.
You're talking about good bacteria?
It's a good thing I'm a chemist. Otherwise, I'd have felt stupid after saying that. All right.
You know what's better when Adam goes, what?
Oh yeah. So where were we at? Yeah. So side note, right? Why does this reaction happen? Why don't they go end to end to end to end? Part of it depends on concentration, but remember, two molecules have to collide in order for a reaction to take place. Yeah, and so they're always like next to each other. So that's one. And then it's the closing of a 5-membered ring or 6-membered ring, and the closing of a 5 or 6-membered ring happens fairly quickly. 5-membered rings usually close a few thousand times faster than 6-membered rings, just because the angle of attack is faster. Okay. Good. So that's one way you can make a ring. Here's another one. This is called a Robinson annulation reaction. An annulation just means make a ring.
That's it for Claisen reaction?
What?
That's it for Claisen reaction?
That's it for Claisen reaction.
So like everybody has made up a reaction.
I can't hear you, boo.
Named after himself.
I heard him. Shush your mouth. Let's finish. We got 15 minutes. So and this one's important. This is your lab. Yeah, Robinson annulation. So this is a Michael reaction, usually, plus an aldol reaction. So here's our example. Remember, aldol reaction is alpha beta unsaturated conjugate addition reaction. So this is my, what am I doing here? Yeah, okay. That's my alpha beta unsaturated, right? And then I'm going to have this ring. And then we're going to have a hydrogen here. And then this is under basic conditions. So the base will abstract this hydrogen and form my enolate. And so, gosh, I didn't mean for it to go that far. That'll form, I'm going to go down on my mechanism and I'm going to draw across. So we're going to go like this, and then we'll have to, I'll draw the product last. I'll have this, right? That's my enolate. And then this will collapse. And the way these things usually go is it'll tack there. Unless it's an aldehyde, then it may attack the carbonyl group. Right? The ketones so tend to be slower reacting than aldehydes. So in alpha beta unsaturated reactions, they tend to, if it's a ketone, it tends to go by beta addition. Okay? So that causes this chain of events. And so we end up with this. Like that. And then that goes to form, because it's enol, it'll go to back to its keto form. Like that. Now you can do an aldol reaction, all right? And what we're going to be looking at is this. 1, 2, oh, sorry, I'm going to go the other way. 1, 2, 3, 4, 5, 6. All right. Now there's 2 alpha hydrogens here. One can't react to form a ring, because if you start where the number 3 is, you get a 4-membered ring, and there's too much strain that slows it way, way down. So instead, it'll come from the number 1, what I numbered the number 1 carbon. This is my nucleophile. And so what ends up happening is you get an enolate formed. More OH minus, right? Get rid of a little bit of this arrow. I'm trying to jam it all in here, but maybe that was a mistake. The OH minus attacks this hydrogen, and then I form the enolate. All right, I'm going to go down. Just can't fit it all on there. I thought I could. I actually don't have this drawn in my notes, so I just assumed it wouldn't take up this much space, but I'm drawing everything out. So that's going to do this. And then number 1 attacks number 6.
Huh?
Number 1 will attack number 6.
Yeah.
Right? Because from 3, it's too short of a distance. So this is what we have, right? 1, 2, 3, 4, 5, 6, right? So if this is 5 and 6, I'm putting a 6-membered ring in place. So I just draw another ring. I'm not going to worry about like exactly how I have to reshape it. I just know it's a 6-membered ring. So I draw the 6-membered ring in place after I number it. Now I have 5 and 6 numbered. So where's 4, right? 4's here. 3, 2, 1. So what's on number 2? Right. So number 2 is going to have the carbonyl back like this. And then what's on number 6? Be an O minus, right? Again, this is the aldol. It's an aldol product, but it's cyclic. So that's what makes it hard.
But would it turn to an alcohol?
What's that?
But it will turn to an alcohol?
Yeah. So depending on whether or not you heat it or not, right? If you heat this, yeah. So this can do 2 things. One is it can stop here. Much easier to draw it once you know where everything's supposed to be. Or if you heat it, so you can add H plus to it, or you could heat this. And then you get the condensation product. Like that. So one's the aldol product, the lower one's aldol. And this is aldol condensation. And I don't know what made me think I could fit that in the square on the right, but it looked like it would fit in my head. So let's do this. Shrink it a little bit.
Okay.
Yeah.
Is this reaction of fire or rain as the reactants?
A what?
A rain?
No. It just forms a ring, is all. I did this one because this is similar to what you did in your experiment. Huh? Lab. But you do need to know how to pull these things apart in your head. So let's say you wanted, and I'll stick with the ring theme. Let's say you want to make this. What were the 2 reactants that formed that? Right? It's actually easier than maybe you suspect. But.
Is there okay, I'm assuming there was an OH in the middle.
Another 3 oxygen.
Yeah, there's 3 oxygens that condensation happens.
So, there should be an OH here somewhere, right? Like here.
Yeah.
There's 1, 2, 3. But remember, this was a ketone before. So one of the things to remember when you're pulling these things apart, you know where the oxygen is. So now you know where the ketone is. So it's going to be like here. And on this side, that's when the oxygen's going to be, right? So you know that. What else do you have?
Well, there was probably aldehyde.
But you had to have the Michael reaction too, right?
Uh-huh.
The Michael reaction, and so that means here, right? This is the new bond as well. So this guy is a new bond that was formed here. If you look at this one, it's between. This is the original ketone, not the alpha beta unsaturated one, but the original ketone, right? So it was added between 1 and 6 and 4 and 5. Like this is where the split was in this one. Right?
So that one, so I know it's the bond's added right there, but the one to the side of the carbon, so right there should be the alpha carbon, right? To the top.
This one here. Here.
Right
Alpha.
there,
That's
right
alpha,
there.
yeah.
That should be the alpha carbon.
Yeah, so this is split like this. And then what you do is you can figure out what the reactants were once you figure out where it splits. Because once you figure out where the reactant is, then you're going to have something that looks like, on one side you have this. It's a diketone. Right? And then on the other side, this is going to be a double bond here. So if you were to just number it, 1, 2, 3, 4, like that, 1, 2, 3, 4, like that, you go 1, 2, 3, 4. On between 1 and 2, oh, I had a double bond. That's unfortunate. And then on 3, I have this. What do I have on 4? It's that. This is 1, 2, 3, and 4. Again, numbering makes a huge difference in these, because then you can just, once you know how many carbons there are in your linear portion of your molecule or your chain or your ring, you just draw it and then you add things to it. Don't try to eyeball it and guess where it was at. That'll be painful. Have the Robinson annulation in there twice.
You got 7 more minutes. We got to finish this.
Well, I'm just going to tell you to read this section. There's a little section on the malonic. I think it's acid ester. Oh, it's the malonic ester synthesis. And the malonic ester synthesis is an alkylation reaction, but it could be used in a Michael reaction. It could be used in a lot of stuff. And malonic acid is this. Just so you knows. It's a dicarboxylic acid. So this is malonic acid. And then the malonic ester is just RO. C-double-bond-O, CH2, C-double-bond-O, and then OR like that. So that's malonic ester. It's a diester reaction. And then that's the most acidic alpha. It's the only alpha, in fact. Right? And this is used for alkylation reactions. Put the Y in there. With alkyl halides, so R like Br like that, or Rx if you want to generalize. And then they usually, after the alkylation reaction, usually do a decarboxylation. We talked about that before. Yeah, it's a lot of steps, but it's the same kind of things I've been looking at. Take out the alpha nucleophilic attack, and then the decarboxylation reaction, just to give you a, let's see, where do I have one? That's a good example. The decarboxylation reaction. Oh yeah. So when you're done with this particular reaction, you're going to have something that looks like this. A beta keto ester like this, right? And then typically what happens is you use like H plus and H2O or OH minus. And if you use H plus H2O, what you're going to end up with is beta keto carboxylic acid. And I'm going to draw this differently, actually. Okay. I'm going to draw like this. Like that. And the reason for drawing it like that is because what happens is this. Let's see. I think I'll draw it like this. Just wipe them down with Clorox wipes. Cool.
Put some myself in
I'm missing something on this. Hang on.
Show me different ones. Oh, no, at least. Okay.
No, there's not.
even know chemistry.
No, I have. Oh, god dang it! I know what's wrong. I forgot a carbon in the middle. I'm like, this doesn't work. Like everything's. Did you ask me that already?
I was like, I got a dot for down the test.
Oh yeah, huh? Well, now you know why it's important. So yeah, sorry, my bad. But it's true.
So carbons aren't that important?
I should have been trying in carbons.
Okay. Almost like, where are those electrons going? It makes no sense at all. Which is what I probably said when I saw your tests. I'm like, where did those electrons go? All right. There, we're better. Like this, that. So, oh, sorry, like this. So the left side becomes this. And the right side becomes CO2. And this is a enol, because that's a carbon, not an oxygen. That's just a bad habit. Sorry. It's an enol, and then it reverts back to its ketone form.
Oh, that makes sense.
And it can also happen. It can also happen from the carboxylate, which I don't have time for, but you still have to know. So you can also do it from the carboxylate ion. That's the one I think I showed in class the other day. I can't remember exactly how I showed it. Maybe I showed this one, but drew it right. Like that, right? And this one's actually easier to draw because it's just this. It just decomposes. And you end up with this enolate plus CO2. And then that forms a ketone from there. Picks up a proton, forms a ketone form. Cool. I think that's it, actually. There's a few other little reactions in there that are all basically the same, but you need to like look at them with the chapter. Look at the summary of reactions, but all the mechanisms are covered for sure.
Oh, really?
What's that number for?
There's a reaction list? Great.
Who said that?
Hey, Doc, can I do that TMS thing?
What's CMS?
Stop recording. Yeah.